For a warm-up, Chris starts with $200 and spends half the current amount of money each day. How much money will Chris still have after a week? Well, what do we know? Chris starts with $200 and spends half. So we know that the dollar amount should decrease each day. And we're going to be doing this for a week, which is 7 days. So let's think, how much money will he have after a week? Well, we're starting with $200. So for day one, half of 200 is 100. Half of 100 for day two would be 50. Half of 50 for day three is 25. And half of 25 for day four is $12.50. Day five, we're going to have half of that $12.50, which would be $6.25. Half of that for day six is 3.125, and then half of that for day seven is 1.5625. Now this is money, so how much money would Chris have? Well, that would be $1.56. So each day we multiplied by 1/2. Well, remember, repeated multiplication is represented by an exponent. So we could have written this a little bit simpler. We started off with 200. We multiplied by 1/2 7 times. So we could have written it as 200 times 1/2 to the 7th power and ended up with the $1.56. So what was important? Here's our starting amount, the 200. What we were doing it for our multiplier, that was half, right? So multiplying it by 1/2, and because that number was less than 1 but greater than 0, we knew that our total should be going down. And the 7 represented how many times were we multiplying by that 1/2. So we have a way of writing an equation, an exponential equation. So again, your ending amount we're going to call y, right? Your result. A is your starting amount, or think of it as your y-intercept, right? B here represents how is it changing? Is it growing or decaying? Increasing or decreasing? It's growing if the B value is greater than 1. It would be decaying when the B value is less than 1 but greater than 0. And then our time period, we're going to call that x, right? And we can measure time a variety of ways. So let's see if we can use this to write some other equations to evaluate and solve different scenarios. Here we have a ball being dropped from a height of 100 feet. On each bounce, the ball rebounds to half of its previous height. Find the height of the ball after it hits the ground 4 times. Well, what do we know? We have an initial height of 100 feet, and it's rebounding half of its previous height. We also know that it's going to hit the ground 4 times. That's our time period. We want to figure out the height of the ball. Well, if we're thinking about this, our result for height, you can use a question mark to represent that, or h, is equal to 100 times 1/2 to our time period, which is measuring 4 bounces. So if we're going to evaluate this in our calculator, we would type it in just as we see it. And remember, to show that you have an exponent, use the caret key. And so what would our height be after 4 bounces? 6.25 feet. Here's a scenario. In June, a 5th grade class started out with 5 mealworms for an experiment. The population of worms will triple every month. How many mealworms will the class have for their experiment in 3 months' time and in a year's time? Well, what do we know? The class is starting with 5 mealworms, and it's tripling every month. That means our multiplier is 3, and we're measuring in months. So our first time period, 3 months, that's representing our exponent. So the population P comes from 5 times 3 to the 3rd power. And again, use the caret key for the calculator to evaluate that. How many mealworms is it? Well, that's 135 mealworms. Now, after a year, how many mealworms would exist? Well, the starting amount is still the same. The multiplier is still the same. The time period has changed. And I don't want to use 1 because it's 1 year. We're measuring in months. So how many months are in a year? Well, that would be 12. So the exponent I need for this problem would be 12. And again, use the caret key to evaluate that in the calculator. We're going to end up with 2,657,205 mealworms. Now, this is the model predicting, right, based on the number of months. And we said before, models are great until a certain point where in real-world context, they don't necessarily make sense. So do you think we'd really have that many mealworms in a year? This equation is not taking into consideration the death rate of mealworms. This is just the growth rate. So we know that this would have to be adjusted in the real world because of that. Here's an example. A certain type of bacteria doubles in population every 6 hours. Given that there were approximately 100 bacteria to start with, how many bacteria will there be in a day and a half? Well, what do we know about the problem? It's doubling. That's our multiplier. And it doubles every 6 hours. That affects our time period. We're going to have to measure things every 6 hours. We also know that we started with 100 bacteria, and we're going to be measuring this for a day and a half. Well, again, we're measuring in hours. So how many hours are in a day and a half? One day is 24. Half of that would be 12. 24 and 12 is 36. We know we're talking about 36 hours. So I'm writing my population equation. I could say P equals 100 times 2 to the power of, now many of you would say, well, 36. But remember, it's every 6 hours. So I have to take that 36 and split it into 6-hour time periods. Well, 36 divided by 6 is 6. That's the exponent needed to evaluate this situation. So what would the population be? That would be 6,400 bacteria. And that's only after a day and a half. In this situation, we're dealing with a substance. So iodine-131 is a radioactive substance that's used to help medical equipment capture images of the inside of your body. Radioactive substances have a half-life, which means that they break down to half their original size over time. Iodine-131 has a half-life of about 9 days. If 20 milligrams of iodine is given to a patient, how much is left after 27 days? Well, what do we know? Half-life. Half the amount stays with you over a certain time period. So our multiplier is 1/2. What's the time period? Well, it says 9 days. We're going to have to measure this in 9-day increments. That's going to impact your exponent. We know the starting amount of iodine is 20 milligrams, and we're measuring this for 27 days. So again, if we think about how much iodine is left, we're starting with 20 times 1/2 to the time period. How many 9s fit in 27? Well, that would be 3. So that's the exponent we have to use to find how much iodine is left in the system. So how much would be left? Well, that would be 2.5 milligrams of iodine after 27 days. So you're going to be practicing this objective again on your own. So underline what you know, circle what you want to know to help write an equation to model the situation, and then you can evaluate it accordingly based on the time periods given or a starting or ending amount based on your situation.